As you're listening to these words, a star is being born in the deep trenches of space. And at that exact same micro-moment, in some distant, nameless galaxy, another star is dying, exploding with such violent force that its light will travel for billions of years, but it might never actually reach the Earth. We are talking about 4,000 new stars, taking their first breath every single second. That's 4,000 stars, since I started this sentence. It is a number so massive that our human brains simply flat out refuse to process it. We like to think we know the cosmos. We look at beautiful photos of nebulae, read about black holes, and hear about the universe expanding. But there's one simple question that can absolutely wreck everything we think we know about ourselves. How many stars actually exist? Not roughly, not at least, but how many are really out there in that infinite abyss we call home? When scientists finally tried to answer this honestly, they hit a wall. The answer isn't just a big number, it's a total reality check for our egos. Let's look at the official numbers first. Most textbooks will tell you our galaxy, the Milky Way, has between 100 and 400 billion stars. That sounds impressive, right? A 1 followed by 11 zeros. Now, take those stars and multiply them by the 2 trillion galaxies we think are out there. You get a number that's basically impossible to visualize: 200 sextillion stars. But here's the kicker. That number is probably a lie. Why? Because that estimate is based only on the observable universe. Think of yourself as an ant sitting on a balloon. You can only see a tiny patch of rubber around you. To that ant, that patch is the whole world. But the balloon is massive, and it's being blown up faster than you can ever crawl. There are parts of that balloon that the ant will never, ever see, because they're moving away faster than light can travel. We are that ant. Our observable bubble is just a tiny fraction of what's really out there. The real number of stars could be trillions of times higher, or it could be literally infinite. And it gets even weirder when you realize how we've been counting. For years, we only counted the bright stars, the showstoppers. But then we discovered red dwarfs. These are small, dim, long-lived stars that make up about 70% of the whole population. They are so faint that even the ones closest to us are invisible without a massive telescope. In 2012, we realized some galaxies have 20 times more of these dim stars than we thought. Not 20% more, 20 times more. Back in 2003, the Hubble Space Telescope pointed its lens at a tiny, empty patch of sky. It was no bigger than a pinhead. It stared at that nothingness for 11 days. When the data came back, that single empty pinhead held 10,000 galaxies. 10,000 galaxies, in a spot where we thought there was absolutely nothing. Later studies showed that 90% of the galaxies in our reach are too faint or too far for us to see, even with our best tech. We are literally blind to 90% of our own neighborhood. But here is the real mind-bender. When we look at stars, we are looking at ghosts. Light takes time to travel. When an astronomer looks at a galaxy 10 billion light-years away, they aren't seeing it as it is right now. They're seeing it as it was 10 billion years ago. Those stars might have exploded or collapsed eons ago, but their light is still hitting our eyes. It's like looking at a photo of a city where the skyscrapers, the medieval castles, and the prehistoric caves are all visible at the same time. The universe we see is a messy, distorted collage of the past. We are living in a beautiful, terrifying hallucination of time and scale. We're standing on a dust moat, trying to count the grains of sand on a beach that never ends. And while we're busy counting, we're starting to realize that each one of those grains of sand is actually a thermonuclear bomb of unimaginable power. We're not just in a peaceful ocean of lights. We're in a nuclear furnace. In the next part, we're going to dive into the absolute violence of these stellar monsters and see what happens when the giants start to wake up. Now, we need to look at what those tiny points of light actually are. We have this peaceful image of the night sky, a silent blanket of diamonds. But the reality is a nightmare of physics. Every single star you see is a raging, screaming thermonuclear furnace. We aren't looking at a quiet ocean of light. We are looking at an infinite field of nuclear violence, where matter exists in states that would melt your brain if you tried to touch them. Take our own sun as a baseline. We think of it as a giant, powerful master of our system. And in its core, temperature hits 12 million degrees Celsius. The pressure? It is 860 billion times higher than the pressure on Earth. Every single second, our sun turns 600 million tons of hydrogen into helium. That process releases energy equivalent to the explosion of 100 billion megatons of nuclear bombs. Every single second. And here is the scary part. Our sun is officially classified as a yellow dwarf. It is a medium-sized, average, quiet star. In the grand hierarchy of the cosmos, our sun is basically a statistical nobody. Astronomers have a system for this, classification using letters like O, B, A, F, G, K, and M. The sun is a class G. But on the top of that list are the class O stars, the blue giants. These things are monsters. Their surfaces burn at over 30,000 degrees. They are so hot that most of their light isn't even visible to our eyes. It's blasted out as deadly ultraviolet radiation. These giants live fast and die young. While the sun will live for 10 billion years, these blue monsters burn through their fuel in just a few million years before they go supernova. They are the ultimate cosmic live fast, die hard story. But size is where the universe really starts to flex. Most of the stars we see, about 70% of them, are red dwarfs. They are small, dim, and long-lived. In fact, our closest neighbor, Proxima Centauri, is so dim you can't even see it without a telescope, even though it's only 4 light-years away. But then, you have the hypergiants. These are objects that defy imagination. And the king of them all, Stephenson 2-18. Located about 20,000 light-years away in the constellation Scutum, Stephenson 2-18 is a red supergiant that makes everything else look like a joke. Its radius is more than 2,150 times larger than our sun's. Let that sink in. If you put Stephenson 2-18 in the center of our solar system, where the sun is right now, its surface would not just swallow the Earth. It would swallow Mars. It would swallow Jupiter. It would swallow Saturn. It would reach far out into the deep, cold darkness past the ringed planet. You could fit billions of our suns inside the volume of this one single star. It is a mathematical fact, but it feels like a cosmic error. And yet, even a titan like Stephenson 2-18 is just a tiny speck when you zoom out to the scale of the whole galaxy. Most of these stars aren't even alone. While our sun sits by itself, Up to 80% of stars actually belong to binary or multiple systems. Imagine a planet with 2 or 3 suns in its sky, gravitational chaos, shifting orbits, and unpredictable seasons. Every star is a potential world, and every world is a potential home for something we can't even begin to imagine. But the story of a star doesn't start with a giant explosion. It starts in a stellar nursery, a massive, beautiful cloud of gas and dust like the Orion Nebula. Deep inside these clouds, gravity begins to win. A tiny pocket of gas gets a little more dense, so it pulls in more gas, which makes it heavier, which makes it pull in even more. It's a feedback loop of pure physics. As the core shrinks, it heats up. When it hits 10 million degrees, the nuclear fire ignites. A star is born. This is happening right now, thousands of times every second, all across the universe. The universe is a factory of fire. It is constantly churning out these massive, beautiful, and lethal reactors. But eventually, every fire has to go out. And when a star, especially a monster like the ones we've been talking about, runs out of fuel, it doesn't just fade away quietly. It dies in a way that can destroy entire solar systems. But as we've seen, even the biggest fires must eventually burn out. And in the universe, some things are much more dangerous when they are dead than when they were alive. When a massive star, one at least 8 times heavier than our sun, runs out of fuel, it doesn't just fade away. It collapses under its own weight in a fraction of a second, triggering a supernova explosion that can outshine an entire galaxy. But it's what's left behind in the smoke and fire that truly defies common sense. Imagine taking a star twice the mass of our sun and crushing it down until it's only the size of a city. We're talking about an object 20 kilometers wide, containing the weight of 500,000 Earths. This is a neutron star. The density here is so extreme that a single teaspoon of this material would weigh billions of tons. If you could somehow stand on its surface, your weight would be 20 trillion tons, and you'd be crushed into a layer of atoms thinner than a sheet of paper instantly. Because of a law called the conservation of angular momentum, these dead stars spin at terrifying speeds. Think of a figure skater pulling in their arms to spin faster. A neutron star does this on a cosmic scale. Some of them rotate hundreds of times every single second. We call these pulsars because they blast out narrow beams of radio waves like cosmic lighthouses. When these beams sweep past Earth, we hear them as a rhythmic, perfect ticking clock. In 1967, the first one ever found was so precise that scientists briefly wondered if they had found a signal from an alien civilization. They even nicknamed it Little Green Men. But there is a specific type of neutron star that is even more frightening: the magnetar. These are objects with magnetic fields so powerful, they are a quadrillion times stronger than Earth's. A magnetar's field is so intense that it actually warps the structure of atoms. Normally, atoms are spherical, but in the presence of a magnetar, they are stretched out into long, thin cigar shapes. Chemistry, as we know it, simply stops working. Magnetars are notoriously unstable. Their crust is under such pressure that it periodically cracks, creating a starquake. These quakes release more energy in 1/10 of a second than our sun produces in 100,000 years. In 2004, a blast from a magnetar 50,000 light-years away hit our atmosphere. It was on the other side of the galaxy, yet it was strong enough to ionize our upper atmosphere and jam radio communications. It was a silent, invisible bullet from the past, reminding us how vulnerable we really are. And then, we have the ultimate victors of gravity, black holes. If the dying star is massive enough, not even the density of neutrons can stop the collapse. Core continues to shrink until it becomes a singularity, a point of infinite density where time and space, as we know them, simply end. Surrounding this point is the event horizon. This is the true point of no return. Once you cross it, the escape velocity required to get out is higher than the speed of light. Since nothing can go faster than light, nothing ever comes back. In the center of our own Milky Way sits a supermassive monster called Sagittarius A star. It has the mass of 4 million suns. But even that is small compared to the giants in other galaxies, like the one in M87, which is larger than our entire solar system. These objects aren't just holes in space. They are active engines of destruction. When matter falls toward them, it heats up to millions of degrees, glowing with a light so bright, it can be seen across the entire universe. We call these quasars. A single quasar can shine hundreds of times brighter than all the stars in its galaxy combined. It's a terrifying cycle. Stars are born in beautiful clouds of gas. They burn with nuclear fire, and then they transform into these gravitational ghosts that haunt the darkness. We are surrounded by billions of these dead objects. Some are ticking like clocks, some are waiting to burst with gamma radiation, and some are simply waiting for anything to get too close. We live in a temporary window of light, between the birth of the first stars and the final reign of the black holes. But how long do we really have? And what happens to us when the last star finally flickers out? In our final part, we're going to look at the cosmic clock, the stardust legacy in your own blood, and the ultimate fate of everything that ever was. If the sheer size of the universe didn't make you feel small, then the scale of time certainly will. We know today that the universe is roughly 13.8 billion years old. To understand this, astronomers often use a mental trick called the cosmic calendar. Imagine the entire history of the cosmos compressed into a single calendar year. The Big Bang happens on the very first second of January 1st. Our galaxy doesn't even begin to form until March. Our solar system doesn't show up until the beginning of September. Dinosaurs? They don't appear until Christmas, and they are wiped out by the day after. And the entire history of human civilization, every war, every invention, and every person you've ever known, fits into the final few seconds of December 31st. We are a blink of an eye in a cosmic year, a brief spark between two eternities. But the calendar doesn't stop today. The future of time is much, much longer than its past. As we've seen, everything in the universe is in a constant state of change. In about 1 billion years, the sun's increasing brightness will cause Earth's oceans to evaporate, turning our blue marble into a desert. In 5 billion years, the sun will run out of hydrogen and swell into a red giant, likely swallowing the Earth entirely. Eventually, it will shed its outer layers and leave behind a cooling core, a white dwarf. And then, the lights will truly start to go out across the cosmos. We are currently living in the stelliferous era, the age of stars. But the supply of hydrogen gas used to build stars is finite. In about 100 trillion years, The very last red dwarfs will run out of fuel and flicker out. The universe will grow cold and dark, populated only by the cooling husks of dead suns, neutron stars, and black holes. This is the degenerate era. Matter itself might eventually become unstable. Over spans of time that the human mind cannot even name, every proton in the universe might decay, and atoms will simply dissolve into light and elementary particles. The only things left will be black holes. But even they aren't forever. They slowly leak radiation and eventually evaporate over decillions of years. When the final black hole vanishes in a silent pop, we reach the ultimate end: heat death. No structures, no events, no temperature differences. Just a perfectly uniform, frozen void, stretching into infinity forever. Time itself loses its meaning because there is nothing left to change. It's a heavy thought, a story that ends in total darkness. But there is something profound in the fact that we can even know this. We are the universe's way of looking back at itself. The atoms in your body were forged in the hearts of stars that exploded billions of years ago. Every carbon atom in your DNA, the calcium in your bones, and even the gold in your jewelry, it all came from stellar deaths and neutron star collisions. You are stardust that has become self-aware. You are the eyes that the universe uses to admire its own terrifying majesty. The fact that we are trapped in our tiny corner of space doesn't make us small. It makes our existence a miracle. We are the only beings we know of who can look at the infinite and ask why. We are a brief, brilliant moment in a timeline that stretches for trillions of years. Even if we never leave our galaxy, or even if we never hear back from the great silence, the act of searching for the truth is what defines us. So, tonight, when you look up at the stars, don't feel like you're in a prison. Feel like you're in a theater,